Please take it away.
Okay, thank you, Roman, and thanks to everybody for coming this evening. I go by Beef. Like you said, I'm in the Fernandez lab, and my PhD is in biochemistry. It started out as a biology, but I started gravitating towards data science. And I'm going to be presenting some of the applications work using machine learning in the field of metabolic phenotyping. So perhaps a very good place to start is to really start from the central dogma of biology. And we are all quite familiar with these, I would imagine. So from the DNA to the RNA to the protein, and which essentially forms the basis of the revolutions of the genomics, the transcriptomics, the proteomics, but there's actually more. And metabolites is actually one of those biomolecules that are very important. In fact, it's the closest that we have to the phenotype. And metabolites engage in, of course, interactions that essentially decides life in so many ways. So when I talk about metabolism, there's just so much interactions going on, and we know very little about what's going on. But it's also always very useful, especially when I'm speaking to a diverse audience like this, is to really bring out intuition pumps. And one that might actually help here is to really think of metabolism as a metro. And just like you have your matter metro, you can think of your metabolic pathways as your metro. So if we zoom in, let's see, if we zoom in now on, let me try and get the laser pointer, if that will help. So if we zoom in on, let's say, the yellow line, for example, you can think of the lines as the major pathways, and you can think of the key metabolites as the railway stations. In this case, C monophosphate, C monophosphate, and you can, of course, then what happens is that biochemical reactions essentially takes place between stations. So the same way, there's going to be chaos in the metro if you have power out in the city or something terrible happening. Anytime you have a diseased system, there's going to be a reflection in a person's metabolism. So that actually underlies how powerful your metabolic system is. And to really take a peep or kind of like understand what's going on, we do metabolic phenotyping. We phenotype metabolites to understand what's really going on. And the methods that are actually important for doing this, the various methods, but the predominant one is methods in NMR, methods in mass spec. Basically, you get what we call features when you identify these compounds. NMR and mass spec are quite different in the way they do things, but the whole point is to go from features to actually identify metabolites. So this is kind of like a general definition of metabolic phenotyping. You are essentially acquiring chemical data, and that chemical data, it's a lot now that we have really tools to generate them in a high throughput fashion. So basically, we now need statistical tools, machine learning tools, to really identify what chemical signatures is associated with disease conditions, particular treatment, and so on. Okay, so the scope of my talk today is going to be sort of in the spirit of data science. I'm going to start first with the classification and regression tags. Next, I'm going to talk about the longitudinal metabolomic datasets study, basically. I'm going to touch briefly on interpretable machine learning. And then finally, this is going to be the very short part of my talk because I'm just getting started with this. We're going to look at deep unsupervised learning. So let's get started. Detection and staging of kidney cancer with urine-based metabolomics. Okay. In this study, what we actually did was to try to detect kidney cancer, specifically renal cell carcinoma, which is a predominant subtype of kidney cancer in urine samples. Okay, so we all know what our kidney does. helps us maintain the body homeostasis. It does that by removing excess waste, toxins, excess water from our system. And these are the incidents of kidney cancer. It's the 5th most prevalent type of cancer in female. It represents 3% of all adult malignancies. In male, it's the 7th most prevalent. It represents 5% of all adult malignancies. And of course, like I said, RCC represents most of these kidney cancer cases. And of course, the sad news is that thousands of people are actually dying of this disease, like so many other cancer. So how do you diagnose this? Well, the diagnosis essentially involve imaging tests, biopsies and things like that. And it comes with its own complications, with its own issues, with its own downside, like we know. And one is that they sort of predispose people to be diagnosed late because it's actually not convenient. And the goal, like I said previously, is to develop a urine test that actually makes it easy to really detect this. Okay, so now this is the cohort that we worked in, that we worked with. So it's a multi-platform metabolomic study, and so we did NMR and mass spec, and these are the samples that we would use. And the first thing that was actually done was to retain overlapping samples that are present in both mass spec and NMR. And that actually led us to controls of 174, RCC samples of 82. And anybody who has done machine learning in biomedicine would of course realize how messy things can get very quickly with things like co-founders. And we got our fair share really at the start of this study when we realized that all samples, all control samples, healthy control samples were collected in the clinic. But it turns out that some kidney cancer samples, urine samples, were collected in the operating room, which has some somewhat different methodologies, and some are collected in the clinic. Okay, so what we did at this stage was to separate out the operating room samples to form the basis of the test cohort, and we retained the clinic samples to form the part of the model cohorts. Okay, and then we are left with 175 controls, 31 RCC. Remember that the controls are all collected in the clinic. So I used a method called propensity score matching. I'm going to be talking about that in the next slide to essentially match 31 controls to the 31 RCC. They have been pre-selected. So these are all collected in the clinic, while the rest actually form the basis of the test cohorts. So that's how we actually went about doing this. So one thing that I would be doing through the course of my talk is just to very briefly highlight some of the statistical methods and machine learning methods that were useful in some of these studies. And I'm going to start with propensity score matching. Okay, so in randomized controlled experiments or trials, which is the gold standard for identifying the effect of certain treatments, what is really happening is that conditioned on covariates that we have, the potential outcomes are actually independent of the treatment assignment. And that just simply means that the two groups, treatment, no treatment, are not fundamentally different, okay? And the second thing is the point to really make about these kind of studies, that each participant in the experiment, they do have a chance of actually receiving the treatment, okay? So that, of course, goes without saying. Well, these form the basis of the ignorability assumption that we have in causal inference, and of course, it's the basis of why randomized control trials are actually pretty powerful. However, if you are dealing with observational study, first, you can't randomize kidney cancer. I mean, that can't be done. And but then you want to deduce what's really the effect of kidney cancer, right? The way to do this is to sort of estimate the propensity score, whereby you can then predict, in quotes, treatment assignments using certain covariates. Okay, and that's basically the propensity score. And if we can do that, we could potentially argue for a kind of a provisional causality. Again, it really depends on what covariates that we control for, and we could argue for 1.1. With this 1.4, and for our studies too, in this kidney cancer study, 1.2 is also quite old to be true, because by definition, anybody can actually develop kidney cancer. So this propensity score matching was actually used to balance these model cohorts, like I showed in the previous slide. So, but what does this mean in terms of execution? Well, if you want to do normal matching, it goes without saying that two groups typically don't have substantial overlap. So you're going to match age, and then you're going to match sex, and you're going to match something else. It becomes really messy. So the propensity score matching method was used to really match these. I used logistic regression, and the covariates that were used were age, BMI, race, the biological sex, and smoking history. And the propensity score here is the predicted probability from the logistic regression, and then we match both. So what does our results look like? Well, this is actually quite blocking these, but I guess I'm just gonna read this out. So the study called propensity score matching reduces selection bias. I mean, that's the upshot of the plot I'll be showing here. And then in summary, without going into too much detail, it's pretty much obvious. This is the pre-matched group. This is the post-match group. Gender is matched. The smoking is matched. There's improvement in race, and there's no significant difference between the RCC and the control for age and for BMI. So those are the 5 covariates that we actually considered for this method. But importantly, our test cohorts actually have different characteristics that makes it a very good cohort to really test the strengths of the models and, of course, the biomarkers that I'll be selecting. Okay, so now I'm going to go through the machine learning pipeline for this RCC detection. And like I said previously, we have the NMR data set, mass spec data set with feature selection using the model cohorts, using this like t-test filtering. We're removing redundant features with Pearson correlations. And finally, we ended with a PLSDA, what's called a partial least discriminant analysis method to rank the important features in the model cohort, and also random forest to rank the important features using Gini index. And then we picked the features, the metabolites that are the consensus of that are present on both lists, highly ranked. And that essentially gave rise to the biomarkers that we selected, and that is used to tune upper parameter tuning for this machine learning algorithm. And then afterwards, we used the selected biomarkers, we used the tuned model to actually test that on the test cohort. So when we first did that, we had a 10 metabolite panel. And when that came out, it turned out that 8 out of 10 of the metabolites actually increased in the healthy controls. So our clinical collaborator at the time came and said, well, we'll prefer things to increase in the case, that's in the disease, because that's kind of like much easier when you get to clinical trials and whatnot. So then we decided to do a similar pipeline, but just focus now on metabolites that increased in kidney cancer. And that gave us another 5 metabolite panel. And Samyukta, a graduate student in the lab, actually took all these. I mean, at this point, I'm calling the metabolite panel, but they're just features because we don't know what these metabolites are. But she was able to identify about seven of these 15 metabolites, and that formed the basis of the panel that we actually presented in the paper. Okay, so the linear support vector machine actually turned out to give us the best accuracy from all of the machine learning models that we use, with an accuracy of 88%. And like I said, what I'll be doing is I'll be highlighting some of these methods that were actually important in some of these studies. So let's go with support vector machines. So in support vector machine, basically, we want to separate 2 groups. I mean, in this context, I mean, this is a classification problem. With an optimum hyperplane separated by a margin. And so the function essentially is to take samples, instance from a d-dimensional space, and then predict it as cancer or no cancer. And given that we have, of course, training sets, which are labeled, we want to get the form of this hyperplane with B plus weight per hex, and we're all familiar with this. And the way this will be done in the case of an hard margin support vector machine objective is to minimize this squared form of the weights. When we do this, what's happening is the margin, of course, is going to be getting bigger to basically ensure that these differences are pronounced, and it's subject to the fact that the correct prediction was actually made. That is the instance on the right side of this margin. But of course, that's hard margin, but of course, we have a soft margin. In this case, we are going to sort of use a slack parameters that keep tracks of violations of the margin, and that's going to be incorporated in the training objective. So we are going to be minimizing this time, which makes the margin as large as possible. We are going to be minimizing this time, which of course makes these violations of the margin as small as possible. And of course, that's already a contention. So you have this hyperparameter C that you can tune. It's an hyperparameter you have to set when you're actually doing these things, doing training. And of course, subject to the fact that the right predictions have been made. Once you have your function, and once you have your training, you have a model, then you can then classify by just saying it's control if it's on this right side of the margin, is disease if it's on the right side of the margin. Okay, so now let's get back to biology. These are the 7 metabolite panel for the RCC detection. So we have converted this thing from features to metabolites. And I am not going to go through this because of the time, but I would just say that anyone who's interested in the biology of these things can actually pick up our papers and actually read. But I would just highlight that just like I said previously, you can see this is an example of N-acetyl-glucosaminic acid. It's a metabolite that actually increased in the urine sample of the kidney cancer patients, and that from our analogy, you can imagine that that's a key metro station being affected, and of course that immediately gives us suggests that there's actually perturbations of certain pathways, and when we begin to dig into the literature, we begin to see things that has to do with DNA repair, cellular signaling, and of course metastasis. Okay, so cell metabolite panel for RCC detection. But can we actually go a little bit deeper? Can we now focus on the kidney cancer patients cohort and ask the question, can we predict tumor size using urine metabolites, or can we stage our kidney cancer using urine metabolites? Okay, so let's see how that goes. To predict tumor size, what I did essentially was just to do a simple Pearson correlation and then pick a cutoff. 4 metabolites was able to actually meet this cutoff. So you can see this is the relative abundance on the y-axis, and this is the maximum tumor width, which we use as a proxy of the tumor size. And you can see cytosine, dimer, diiodine. These are indicating like perturbations in the nucleotide pathway and so on. But when we actually put this into a regression model, basically elastic net and ridge regression, we had a decent result, an R-squared value of about 0.56. It's not great, but it's actually pointing that there's actually some relationship going on here. And if we were to have other biomolecules to add here, I think the result will have turned out great. But what we did next was then to zoom out a little bit and say, can we actually discriminate between early stage and advanced stage, just with the urine metabolites? An early stage, basically, roughly speaking, we are saying the tumor is confined to the kidney. Late stage, we are saying that the tumor is actually spread out of the kidney. I'm not going to go through the pipeline again. It's very similar to the one I used previously, but we are able to identify 24 metabolite panel that discriminate early stage RCC from advanced stage RCC. And we use numerous machine learning algorithms to try to do this. And a voting ensemble classifier essentially gave us the best accuracy with 87%. I can see I think a person is asking the analytical chemist work. I'm not sure what the question is, but perhaps I should just say very briefly that what's really going on, and I'm skipping, this is just a story, I'm skipping so many things because of the nature of the talk, is, like I said previously, what we have from the instrument is what we call features. And in NMR, you just have like ppm values. There's so many, you can do your HSQC, so many kinds of analytical chemistry experiments you could do. In mass spec, you have retention time, you have M over Z mass over charge values, and then the work of the analytical chemist is basically to identify what those outputs are, what those features are, and that is a big part of what we actually do in this study. Okay, voting ensemble method. So again, in the spirit of what I said previously, I'm just going to be highlighting some of the methods that actually work quite well, and this is very much straightforward. The decision of a T classifier, so a particular classifier is actually 0 or 1, and if a T classifier chooses a particular class, then we say it's 1. If it doesn't choose that class, it's 0. And what the ensemble decision algorithm essentially does is to pick the class that actually has the maximum number of votes. So it's kind of like a voting system, and sometimes it does work. Okay, again, back to biology. This is very similar sort of a presentation of the summarization of the biological result from the previous study. In green, these metabolites are increasing in advanced stage of RCC. In yellow, they are decreasing in advanced stage of RCC. And I'm just going to use glycine as an example. So glycine, urinary glycine, is actually decreasing in advanced RCC. And when we dig into the literature, we realize that there have been so many studies that have shown that glycine are decreasing because they are being shunted into purines and pyrimidine biosynthesis. Okay. Again, for folks who are interested in the biology, we discussed some of these things at length in our paper. So so far, I've been talking about a single time point, this kidney cancer study. But what about if we have a longitudinal metabolomic study? What if we have multiple time points, which is much more ideal in certain circumstances? So this is going to lead me to my next part of my talk. In this case, I am going to be talking about lipidome remodeling dynamics in a mouse model of ovarian cancer. So let's get this started. Again, we're having some blocking this, but I'm going to read it out loud. Ovarian cancer. Oh, it's gone. So ovarian cancer is one of the most common and deadly cancers in women worldwide. That goes without saying, we all know that. It starts from the fallopian tube, it spreads into the ovary, goes into the abdomen, and of course, it's mostly disaster afterwards. But 1 in 78 women are at the risk of developing ovarian cancer during their lifetime. 1 in 108 has a lifetime chance of dying from ovarian cancer. And this is complicated because at the early stage, sometimes it's asymptomatic, and when you begin to have symptoms, it's the vague symptoms. So it's really tough. And so the goal in the field in general is to look for an early stage metabolic diagnostic panel. But the primary goal of this study is to really study the dynamics. In this case, we are looking at the lipid dynamics of this disease over time. Okay. So we are using a mouse model called the DISA-P10. So it's called the DKO mouse in the field, and it has molecular and phenotypic similarities with human. So this has been quite established in the field. And then we then take a control of that mouse. So we compare both mass spec based metabolomics was done. About 1,000 analytes were actually annotated. And then now we begin to try to tell the story using data science to see what's really going on as the ovarian cancer progresses. Okay. So the lipidome actually changes in response to the ovarian cancer. And the lipidome essentially represents the totality of the lipids that are actually present in this case, in the serum sample. So we are looking at the blood. So what I am showing is the clustering of these lipidomic trajectories. So on the y-axis, you have a log-fold change of the DKO metabolite abundance to the control. And on the x-axis, you're seeing the stage being. So this is contiguous, it's progressing. So lifetime stage 1, stage 2, stage 3, stage 4, and to stage 5. And essentially, we now identify about 4 clusters of lipids that have similar trajectories over time. And this is another sort of a presentation of the results. It's the same thing factually, but the thing to point out is when we actually start looking at what the lipids that consist of these clusters are. So cluster A, it contains phosphatidylcholine, phosphatidylethanolamide, and these are phospholipids, okay? And these are phospholipids. They are the predominant metabolites, lipids that are present in this cluster. In cluster B, they just contain only phosphatidylcholines. In cluster C, it contains PCs, phosphatidylcholines, and a degradation product of PE. Okay, and it's quite interesting that one thing to point out is you can see this spike that goes on from stage 1, lifetime stage 1 to stage 2. That seems to be a kind of denominator of these clusters. And the biological reason for that, I'm going to touch on it when I start summarizing this work. In cluster D, on the other hand, you can see the spike in the last phase. So basically from 4 to 5, and that's just towards the end of the lifetime of this mouse. Again, this is comparison between the DKO to the controls. Okay, another thing that was done was to see if we can discriminate between DKO and the DKO control mice, that's the ovarian cancer and the non-ovarian cancer mice, over time using those bins. So basically we have a feature selection, like with removing redundant features, t-test filtering. In this case, I use a random forest feature selection. And then once I select the features, then I use this machine learning algorithm to actually, of course, test the accuracy of the features and the models that were selected. And this is done for the 5 lifetime stages that are actually present. And this is the raw curve of these results. But of course, there's so many things going on, and you won't be squinting your eyes. I've summarized the results in this bar graph. On the y-axis, we've seen the Datasets ROC AUC curve score, and of course, this is showing it for all those lifetime stages. But the thing to point out is these are actually quite a great score for these kinds of analysis. But even much more important is the fact that at the early stages, we are seeing an AUC of 0.8. So this kind of erects a promise of something kind of promising when we start looking at humans. Okay, so prognostic markers. We all know that prognostic markers are actually useful in providing information on the likely outcome of any cancer patient, anybody who's sick. So what we did next was essentially to use some survival analysis methods to investigate what lipids can be predictive of what the cause of ovarian cancer would be in this mouse model. And to do this, we essentially use a survival analysis. And of course, to do that, we have to get a survival function. And the survival function gives us the probability that a mouse survives longer than some specified time. And to do that, we're going to be using a Kaplan-Meier estimator, which essentially is, in this case, showing sort of the probability that a mouse survives prior a time failure time TF multiplied by the probability that the mouse actually survives beyond that time TF, given that it survives up to that time. And the way this is done sort of procedurally is just basically for each time point you're computing to look count the number of death events at time t, and the number of mice at risks of death just before that time t, and then you can then do that and get your curve, your survival curve. And if you have two groups, you can also compare them using a restricted mean survival time analysis, which is just getting the area under the curve. Okay, so we did this for our analysis, and we are able to identify 3 species of PCs, phosphatidylcholine, that are actually quite statistically significant, which means that they are candidates that can be used as a prognostic marker. And the way this was done was just to take all of the decay of animals and then bin that into 2 groups using median splits, high group, low group, and then we did the Kaplan-Meier analysis. Okay, so let me just begin to round up this aspect of the talk by saying that we were able to identify that lipid changes, and this is of course quite hypothesis going in at the early stages, and I showed quite a number of results to support this evidence. We're seeing PC, PE going up. And these are phospholipids. They are important in cellular membrane stability, and that's why we're seeing that. On the other hand, at the early stages, we're seeing ceramides and exoceramides actually increasing, spiking up, and that's evidence of cellular survival, cellular proliferation. But in all, our study was able to show evidences of perturbations in cell membrane stability, cellular proliferation, and of course, cellular survival. So far, I have been talking about, we've been using different machine learning methods to distinguish between groups, did some regression, but it's really important to really state that that interpretable machine learning is really important in biomedicine, because we can't really afford to deal with black box models. We really want to know what's really going on, and that's why I think I should probably present something on that. So this is going to be my next section of the talk, and I will be talking about Shapley additive explanations for really interpreting machine learning models. Okay, so Shapley values give axiomatic solution to fairly distribute payout to players in the game. And Shapley values essentially came up to us to game theory. Basically, it's just a way that tells you how to, again, fairly distribute the contributions of a players in a game to them. And we can actually take this idea and bring it into machine learning, and then begin to think of features as players and think of the predictions as the payouts, okay? And in Shapley value, or what you do, of course, is you compute a feature importance, which is the Shapley value. And the way you do that is to compute marginal contributions of a single feature. And you do this by having subset of features in the model, making prediction with that sample and without that sample, different coalitions, different ways of assigning the weights. You sum that, you have it, that you sort of get the Shapley values. And the Shapley value is great because it actually assures us that science things will be done, and one of them is the idea of symmetry or consistency. And this simply means that if the marginal contributions of, let's say, feature XC and XK, if they are the same, then their feature importance will be the same, and which is exactly what we want. And if the marginal contribution of XC is equal to 0 for, of course, all possible coalitions, then the feature importance will be equal to 0. And even nicely, it has a really nice additivity feature whereby if we take all the single feature importance and sum it up, we can actually explain the behavior of the entire model. And that simply means we can do local predictions, and local explanations or local interpretations and global interpretations. Okay, but then how do we really go about this? If you want to do this naively, the first thing you have to think about is, how do I undo missing features when you're computing these marginal contributions? And of course, this is going to really take an exponential computational time, goes without saying. Well, the solution to this, or one solution to this, is to actually use a tree-based SHAP method, whereby you calculate exact Shapley values by just ignoring decision paths of missing features, okay? And that's just because we're leveraging the tree shape of these machine learning algorithms. And if we can do that, we have an efficient algorithm whereby we reduce the complexity from exponential time to polynomial time. So this was the method I used. I used the true SHAP method, and then I apply it to these machine learning metabolomics problem. But I'll be talking about only one of it today. I think it's actually only one of it that I actually even talked about in the paper. So the first one is a biological sex classification. The metabolomics studying the impact of high-fat diets, and of course, a cancer metabolomics study. Okay. So that's a data split for the training set and the test sets. And the machine learning pipeline on the workflow, it's very similar to what we've seen previously. We do a feature selection with t-tests, fold changes, featuring, transform features. And one thing I did in the paper is to compare the tree-based SHAP explanation with VIP score for partial least discriminant analysis. And the reason why I did that was this is the method that is pretty much predominant in the field of metabolomics. But I won't be talking about that here, but we'll be focusing on explanation of a tree-based model. So using this pipeline, this is the result of our machine learning. So we're seeing the metabolomics data sets that I used, or the study that I used, and we've seen the machine learning models, okay, either it's baseline or it's tuned. But I'm going to be explaining just one of these, and this is going to be this particular one. And the reason why I'm doing that is it's from a data set that actually discriminate between male and female using urine metabolites. So the results was very much easy to explain. There's diversity of errors, because one thing that I also did, and I'll be showing here, is explaining how the machine learning is making the predictions by looking at the errors they are making. And of course, because it has a pretty decent predictive score. Okay, so now let's go to the interpretations. This is called a summary plot, and on the y-axis, this contains the urine metabolites that are important and are arranged in descending order. On the x-axis, you're seeing the SHAP value. This is the impact of those features on the model. If it's negative, it's driving the prediction towards female. If it's positive, it's driving the prediction towards male. Each dot you see here represents a sample. Represent the sample, that's correct, for a metabolite. And each dot you're seeing, of course, it's actually low feature or it's high feature, okay? So, and of course, you can see right off the bat here that a metabolite of the testosterone is actually the most important metabolite for this discrimination, which is why I actually picked it because it's actually quite intuitive for many people. So to really just summarize, we see here that high abundance of this metabolite of testosterone is associated with male predictions, while low levels, so lower levels, tend to be associated with female predictions. Okay. So to really sort of draw some sort of a close at this, let's do a little bit of error analysis. So we have a confusion matrix here, and let's kind of walk through what a typical sample looks like in each of these boxes. Okay, so this is a waterfall plot, and on the x-axis, this is essentially just telling us what the prediction is, and on the y-axis, we are seeing the feature value and the metabolite itself, and we are seeing the impacts of that feature on the prediction. So it's either pulling it towards a female prediction or pulling it towards a male prediction. Again, this is a binary classification problem. And what we can see here essentially is that and these feature values are auto-scaled. So this is a positive high value for testosterone glucuronide, and this is a true positive sample. So this is a male sample that's successfully classified as a male sample. Now, if we go to a false positive, and this is a female sample that was wrongly classified as a male sample. And if we begin to inspect it, so first thing we notice that the testosterone level is actually, it's negative, is low. But then we see that the probability of the prediction is actually very close to females, just about 0.5. Okay, so that also makes sense. So the next is the true negative sample. The true negative sample is a female sample that is correctly classified as female. It has a very low level of testosterone glucuronide, and of course the prediction is female. And finally, we have a false negative sample, and that is a male sample that is wrongly classified as females. It's a male sample, but wrongly classified as female. But the thing is that we actually don't see testosterone glucuronide as any part of any of the top 10 features are important. So the summary from all of this, just showing like the insights you can drive out from actually explaining your predictions. And there's so many things that the SHAP framework allows you to do. You can do things like looking at the impact of two features on predictions in itself through what's called the dependence plots and many other stuff. Okay, so we have looked at kidney cancer detection using urine sample, kidney cardinal staging using urine samples. Next, we looked at ovarian cancer in a mouse model using blood samples. Next, I actually talked about a urine sample datasets to discriminate between male and female, but these are all homogeneous samples, and then you can ask the question: can we actually do this on things like tissue samples? Well, it actually turns out that we can actually do this, and we do that using mass spec imaging and technique, and this is actually going to be something that I am just starting on in the lab. So this is going to be a short part of my talk, and I'm exploring actually analyzing these mass spec imaging data sets with autoencoders. Okay, so mass spec imaging allows us to do spatial metabolomics. And that is, we are mapping molecules on, in this case, tissue samples. Okay, each pixel actually gives us a mass spectra, and in each mass spectra we have spectra peaks, these signatures that tells us what metabolites are actually present, and we can then use that to generate ion images. So these images essentially show pretty much like heat map, showing the prevalence, the abundance of the metabolites on that particular tissue. Okay, but this is an high-dimensional data set. So again, you have like 10 to the 6th pixel, and for each pixel you have like 10 to the 5 M over Z bins, and this is quite a lot of data. And one of the tasks that is quite pivotal when we are doing this, when the chemists are actually doing this analysis, is to do what's called spatial segmentation, and that is to partition a sample into distinct regions of molecularly similar pixels. And this would allow us to see regions that association of regions that has metabolite, that has to do with healthy sections or disease regions, and so on. And one way to reduce the dimension of these data sets, of course, you can try to think about PCA, and which is great, but of course, it's only look for linear associations. So it's a linear transformation process. And then so I then begin to think about actually using things like an autoencoder for this, and an autoencoder essentially, I believe could be, it's based on the neural network. It could be fully connected. It could be convolutional neural network, and you have your inputs, and then you can summarize your inputs into a latent space, and then from that latent space, you use a decoder to reconstruct your inputs. And many people perhaps have played with the various OpenAI tools recently, and one of them is the DALL-E 2. I believe we probably use a variational coder in some of its implementation. But of course, why is it quite useful? It's quite useful because of this loss function it has. Basically, it's going to compare the outputs with the inputs, and that allows it to learn a good summary of the data that is being presented. Okay. A few things to point out is that without your nonlinear activations that you have in a neural network, without this reconstruction loss that I just spoke about, your coder is essentially just a PCA. Okay. And another thing I should point out is the autoencoders, of course, can learn nonlinear interactions and things like that. But for a vanilla autoencoder, of course, there is there's some sort of challenge. The distribution is not centered, it's not continuous. So one of the things I'll be trying hard first is to use a variational autoencoder whereby the learning space is made to form a Gaussian distribution to make it centered, to make it continuous. And then, of course, would proceed with the loss function and perhaps learn a very nice summary of the data in the latent space that would allow us to do a spatial segmentation. And the goal here is just to learn to use variational autoencoders, some other kinds of autoencoders. I'm still actively reading about this and explore that to actually use it for this spatial segmentation. Okay. So I'll be summarizing my talk now because again, I would still like to go back to this metabolism as a metric because it just makes things quite easy to understand. If something nasty happens, like a disease in the system or in a city, let's say terrorist attack, it's going to really mess things up. Okay, and we can pick that up by doing metabolic phenotyping. And these days we have high throughput method that allows us to do it, whereby we get a lot of data sets. And of course, this makes it possible to start using things like machine learning. Like that's how I got into machine learning. Like I said, my background is biology, my PhD is in biochemistry, but there's this data set lying around, and why not just use it more productively? So then in this talk, I've been able to then show various ways that is kind of applied to metabolic phenotyping. So classification and regression tags in my kidney cancer detection paper, clustering and classification tags in ovarian cancer progression, interpretable machine learning with this explaining biological sex classification, and of course this work that I'm just beginning to start with spatial segmentation of mass spec imaging data sets. So with that, I would like to really acknowledge this work that requires a whole lot of people. Okay, so the renal cell carcinoma work, David and Samyukta in the Fernandez lab are the folks who work on the NMR, on the mass spec aspect of this work. I work on the NMR aspect and the data science aspects. Clinical leads are John Petros and Rebecca Hannard, collaborators from memory, and my PhD advisor, Art Edison. For the ovarian cancer study, Samyukta actually worked on the chemistry side of things with the mass spec. Collaborators at Baylor College of Medicine are the folks that developed this mouse model, basically collected the blood samples, and I believe this was actually even done during the pandemic, so it was quite an Herculean task from them. And this study is funded by the NIH. And for the interpretive machine learning stuff, I would like to just thank my heart for feedback, and of course the entire Fernandez lab in general. So thank you so much for listening to my talk.